binomial expansion is what we're going to be looking at today. And that's, you've got a little investigation sheet in front of you. And we're going to kind of work through this together. But binomial expansion is a skill that's really, really important. It's really useful in calculuses. It's really useful in upper level algebras as well. Did you get one of these? All right, so binomial expansion is what we're going to be looking at. So let's kind of start with question number 1 on your sheet there. Question number 1 says, what is x plus y to the 0 power? X plus y to the 0 power would give us 1, right? Anything raised to a power of 0 has a value of 1. Okay? Now, the second one, also really easy. What is x plus y to the first power? It's just going to be x plus y, right? X plus y. Now, take a moment to look at x plus y to the second power. Everybody take a second to expand that. X plus y to the second power means x plus y times x plus y. Multiply that together, and according to the sheet, they want the powers of x to be in descending order. So x squared, then our x, the first term, and then our non-x term. So if we multiply x plus y times x plus y, what do we get? X squared plus 2xy plus y squared. Okay, very good. And then we're taking it to the next step, which would be what? X plus y cubed. So take a minute. You don't have to start over from scratch because we already have x plus y squared right above it. So take a moment to take this expression and multiply it times x plus y. Now this is using the skill that we did yesterday, expanding polynomial expressions, multiplying polynomial expressions. So it gets a little bit trickier as you get higher up the line here. X plus y cubed will give us something we'll look at in just a sec. Students in first and third period this morning found that they weren't quite as good at this multiplying process as they thought they were. X plus y cubed starts getting a little trickier. Okay, so when we multiply that by x, if we multiply this expression up here by x plus y, we get x cubed plus 2x squared y plus xy squared. And then when we multiply by y, we get x squared y plus 2x y squared plus y cubed. Right, is that the individual terms you got? And then we can combine like terms. Right? Is everybody okay with that? When you combine like terms, we end up getting, let's see, let me just do it back out this way. When we combine like terms, what is our final product for x plus y cubed? Read it. Somebody read it to me. Who's got it?
X cubed.
X cubed.
Plus 3x squared y.
Plus 3xy.
Plus 3xy squared.
Plus 3xy squared.
Plus y cubed. Okay, do it one more time. Let's figure out what x plus y to the fourth power is. I'm going to pause. So what we get, x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. We get that by going through a process of multiplying this thing and going through 4 steps, right? It's time consuming. Can we find a method to jump straight to
x plus y to the fourth without having to do all this other kind of stuff. What patterns do you see? Where do you see Pascal's triangle? You're remembering that, right? So you're remembering that. Let's suppose you don't remember that. Remember using Pascal's triangles. What pattern do you see here? What patterns do you see with the x's and y's? What patterns do you see with the coefficients?
The x's count down.
The x's count down, right? So when we're raising something to the third power, for example, my highest power of x is 3, and then it goes 3, 2, 1, and x to the 0, right? What's happening to the y's? The y's are going up, right? So we start with y to the 0, then we go y to the first, then we go y squared, then we go y cubed. Now, if you put 1s in the places where the coefficients are 1, you do indeed have Pascal's triangle, right? Pascal's triangle, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 1 is 3, 3 plus 3 is 6, 1 plus 3 is 4. So we get all of that Pascal's triangle. We're going to put Pascal's triangle up in just a moment. As a matter of fact, it's over there on the board. Okay. So the coefficients, if we continue this pattern, the coefficients of these multipliers come from Pascal's triangle. Right? Y'all remember Pascal's triangle from Algebra 2. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. What else do you notice? You notice anything special about the second coefficient in every expansion? It's the power, right? We're raising something to the fourth power, for example. We'll raise something to the fourth power. Our second coefficient is 4. We're raising something to the third power. Our second coefficient is 3. When we're squaring something, our second coefficient is 2. The first power. So we could expect that the next one is going to be 5 on the second term. Right? So if we're raising something to the fifth power, we've got a 5 in play there. What else do you notice? There's one fact about this that nobody has noticed today without my help. So I want you guys to strain and think if you can see any similarities between all the terms in the rows. Are there any similarities that the terms in each row have in common?
Like the 3 and the 3 are like the same, like in every row. Like the coefficients are like the same, except for like sometimes like the middle one, like on from side to side.
What do you mean by that?
Like the one on the left side in front of that, like x squared.
Okay.
And the one on the right side in front of the y squared. And then if you move down like to the x cubed is the same, and then the 3 and the 3 on that row are the same too.
Okay. Is that going to be consistent with the rows beyond that?
Except for if there's an odd number of terms, except for like that middle term.
Huh. You are going to have pairs except on the even rows. No, the odd rows. So there is symmetry to the numbers, right? That's what you're saying? There's symmetry to the numbers. Good. I see exactly what she's saying now. It's a palindrome. Each line is the same forward or backwards. There's symmetry to the numbers. Is that what you're saying? Okay. All right. What else? What's the degree of all three of these terms? What do we mean by degree? It's the sum of the exponents of the variables, right? So what's the degree of this term? 2. What's the degree of this term? 1 plus 1 is 2. What's the degree of this term? Right, 2. What about this one?
3.
This one?
3.
This one?
3.
3. And the final row?
3.
This one has a degree of 4. All right, so does everybody see that? The degree of each term is the same. That's one of the most important facts that we need to be able to see about this. Okay, because the process is only good if there's little ways that we can check our steps along the way. Okay? Can we check our steps in this process through the patterns that we're seeing? We've already noticed that Pascal's triangle is going to be the multipliers. We've already noticed that the powers of x are descending, the powers of y are increasing. And we noticed that the degree of every term has to be the same. When we're expanding something to the fourth power, the degree of every term is 4. If we're expanding something to the fifth power, the degree of every term is 5. Okay? All right, so using that, I want you to move on to the next step there. Skip on down to 3 and see what you get when you expand x plus y to the fifth power. X plus y to the fifth power is what we're going to use. With me, Peyton?
Pretty hard,
Do what?
I
Man, I was just, for a second, I was wishing I could go wherever your mind was. Somewhere a lot better than college algebra class in the afternoon learning binomial expansion. 3 things that I guarantee that none of you were looking forward to today. Boy, I can't wait till right after lunch. I get to learn binomial expansion in college algebra class. X plus y to the fifth power. Okay? If the pattern continues, and we're going to be using the fifth the fifth row or sixth row of Pascal's triangle, my coefficients are going to be 1, 5, 10, 10, 5, and 1. This is going to be, I'm going to have to write small here. What are the powers of x doing? Powers of x are decreasing. We're going to start with x to the fifth. Next term is going to have an x to the fourth. The next term will have an x to the third. The next x squared, x to the first, and no x values. Okay? But what are the powers of y going to be doing? Increasing from left to right or decreasing from right to left. So we could start over here if we wanted to and do y to the fifth, y to the fourth, y to the third, y to the second, y to the first, and y to the 0. So that's it. I'm done. Now, if you know the pattern, if you understand the pattern that's going on in binomial expansion, and you have Pascal's triangle readily available, or you can produce it really quickly, this is way faster than multiplying x plus y times itself 5 times. Okay? And it's even more friendly or user-friendly or shortcut of sorts if we're doing something like the next thing it's going to ask us to do. But before we move on to that, go ahead and figure out what x plus y to the 6th power would be. X plus y to the 6th power. We're going to need the next row of Pascal's triangle, right? Which would be 1. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15. Then we have the symmetry that Sarah pointed out to us a little bit earlier. That's not going to leave me much room there. Right? Does everybody see where those numbers are coming from the previous row? You're just adding the 2 numbers that are directly above it. 1 and 5 gives you 6, 5 and 10 gives you 15, 10 and 10, and so on and so forth. Okay? What are the powers of x doing? Decreasing. X to the 6th, x to the 5th, x to the 4th, x cubed, x squared, x to the 1st. And the powers of y are decreasing from right to left or increasing from left to right. So I just like to start right here since I'm there anyway. Y to the 5th,
y to the fourth. No, that's 6. That's 5. Let me clean that up. 6, 5, right and small, 4, 3, 2, 1, and 0. Everything here is plus. Okay? Now, what are some of the quick checks that we looked at? How can we check this to make sure that we've done it correctly? Make sure the powers of x or whatever that first term are decreasing. Make sure that the powers of y are increasing or decreasing right to left. And make sure that the degree of every term is what? 6. Okay? So the first term has a degree of 6. 5 plus 1 is 6. 4 plus 2 is 6. 3 plus 3 is 6. 2 plus 4 is 6. 5 plus 1 is 6. And then 5 to the 6th. Okay? Definitely a time saver. Now, how is this going to work if we extend it beyond just working with x plus y? You do the same thing, except instead of using x and y, you use whatever's there, right? So what's that next term? Let's move on. What's the next example? 2x plus y to the third power. Okay? Okay? Who's pretty good at multiplying this in order, right? You're pretty good at this, Jagger?
Very good.
All right, Jagger, I want you to, without using the shortcut, I want you to multiply this. You want to do it too?
Yeah.
Okay. Garrett, you do it just by multiplying it out. I'm going to use Pascal's triangle. 1, 3, 3, 1. 2x cubed. 2x squared. 2x. Y cubed. You're done? Y squared. And y. 8x cubed plus 12x squared y plus 6x y squared plus y cubed.
Yeah, you did.
I'm done, right? Now, I'm going to be faster at this than you would be just because I'm very, very familiar with the process. But you can see that even when you get to a cubic, which is not, you just have to multiply it 3 times, even if you know the squares and have them memorized, it still takes a lot of time to do this. But if you know Pascal's triangle, it doesn't. Okay? How does it work with negative quantities? This one's not on your sheet there, but let's do this one. Y'all ready? Write this one down. Let's do y minus 2x to the fourth. To the fourth power. Y minus 2x to the fourth power. Okay? Start with the coefficients. What are the coefficients for 4? You look for the row on the Pascal's triangle. It has a 4 in the second digit. So that's 1, 4, 6, 4, and 1. Now our x's and y's kind of got turned around here, didn't they? But this is my first term, so what is that term going to do? It's going to start with what power? And it's going to decrease, right? So y to the fourth, y to the third, y to the second, y to the first. Now my other term, my second term here is what? This is where you have to be careful. It's negative 2x. Because binomial expansion only works if there's a plus in the mix, right? So this is the same thing as y plus negative 2x to the fourth. Okay, so I'm going to start here with negative 2x to what power? To the fourth, right? And I'm going to walk it down. This one's going to have, I'm going to have to kind of write this up above because I didn't leave myself enough room. Negative 2x cubed in that one. Negative 2x squared in this one. Negative 2x to the first in that one. Okay. And now I'm going to have to practice the skills that we've been doing the last couple days in class, right? Y to the fourth just stays y to the fourth. 4y cubed times negative 2x is negative 8y cubed x. All right? This next term, 6y squared times negative 2x squared, the quantities being squared. What's negative 2x squared? 4x squared, right? Is positive or negative? Positive because the negative number is being raised to an even power, so that's going to be 6y squared times 4x squared, which is 24y squared x squared. The next term we have negative 2x cubed. That's negative 8x cubed, right? It's negative because the negative number is being raised to an odd power. 4 times negative 8 is negative 32 yx cubed. And then finally at the end we have negative 2x to the fourth, which is positive 16x to the fourth. Okay, any questions there? All right, what's the last problem on the sheet there?
2x minus 3.
2x minus 3y to the fifth power. All right, that's the last one we're going to do. 2x minus 3y to the fifth power. I'm going to close the video because I don't have room to do this here.